All right. Hello, everybody. Today, what we're going to do is talk about what comes beyond white dwarfs and neutron stars. What happens if a incredibly massive supergiant goes supernova? Let's say something that's over 30 solar masses. We think this. Here's what's going to happen. The core mass is going to be that's left over after the star dies is going to be greater than 2.2 solar masses. If a massive enough star dies, the core mass is going to be greater than 2.2 solar masses. Now, let's review a couple things. Remember we said if the core mass of a dead giant is between 0.3 and 1.4 solar masses, we get a white dwarf. And remember what force balances gravity in a white dwarf? That's electron pressure. Electron pressure, the electrons get close enough together, they push back, and that works up to 1.4 solar masses. That's the Chandrasekhar limit. That's pretty much the electromagnetic force. We also said this. If the core mass of a supergiant after the supernova is between 1.4 and 2.2 solar masses, then we get a ball of neutrons called a neutron star, where the strongest force we know, which is the strong nuclear force, is enough to balance gravity if this core, this very, very dense core, is up to 2.2 solar masses. Now, my question for you is this. If the strongest force we know is enough to balance gravity, if it's up to 2.2 solar masses, this core, what force would balance gravity if the core is over 2.2 solar masses? Remember, the strongest force we know only works up to 2.2 solar masses. Well, the answer is no known force. If the core mass after the supernova that's left over is greater than 2.2 solar masses, no force can stop gravity. And if no force stops gravity, what's going to happen to this core? It is going to collapse due to gravity until it's essentially no size. And I mean, that's crazy. And this is where we get to this. We get to some physics here that is not even the physics we have. It doesn't even work for some of the things we're going to talk about. But what I'd like us to do today is something called a thought experiment. Einstein liked to do this. Like, let's say you can't really go somewhere, figure something out that way. Well, you try to reason it out in your head using science, using physics, and you do these thought experiments. So let's say this. Let me show you a core of a dead giant. And let's say here's a sphere here. It's a sphere. Let's say it's a sphere here. I'm drawing it as a circle. So here's a core. Let me get a different pen here. This core is, let's say, 10 solar masses. 10 solar masses. There is nothing that will stop gravity from collapsing it. So, which means this. If we want to represent gravity as green arrows, the gravity here is incredibly strong. The gravity is incredible. This thing is already small enough as it is. I mean, it's just some number of miles across. Gravity is incredible, and gravity wants to compress it down to nothing. And it's 10 solar masses. So no force is going to stop it. So we're going to slow down things. It would happen almost instantaneously, this collapse. But with our thought experiment, we're going to slow this down. And we're going to go here. And we're going to go here with a spaceship. And let's show our spaceship here. I'm sorry, the way this thing looks. So here's our spaceship. And what we're going to do is we're going to go into orbit around this thing in our spaceship as this thing collapsing down. And we're going to be on this spaceship. Let's say this is you. That's you. And this is, let's say, your assistant. Now, you might have John, you might have Joe, you might have Argyle as your assistant for our class. So this is you, and that's your assistant. Let's just say it's Joe, all right? A lot of you guys don't know Joe, but you don't know Argyle. Some of you know John. Maybe you know Joe. If you're in Joe's class, section 4212, you know Joe. So let's say that's Joe. And for those of you who are in section, actually for Argyle, those are in Astronomy 4, so none of you guys even know Argyle, which is just as well. So it could be, so let's say this is Joe, not John. That's you. So one of you is going to go to the surface of the thing as it's collapsing, and one of you is going to stay on the rocket here, going in orbit around. Who goes? Yeah, I can tell. I can't even hear you guys right now, but I know you're saying Joe goes. So let Joe leave here. They're going to send Joe down and put Joe on the surface of this thing as it's collapsing. Now, right now we can say this. There's a lot of gravity on this thing. The surface has an incredible amount of gravity. Let's talk about what the force of gravity is here. Just to show the equation, not that you're going to have to remember it, but the force of gravity is dependent on how much mass two things are, the masses, how much stuff, divided by the distance between the centers squared. So there's going to be a lot of gravity on this thing because it's 10 solar masses. And also what's true here is this. The distance between the center, from the surface here to the center, this distance right over there, it's very small. So because one of these masses is very high, Joe's mass is not that high, but the mass of this thing's incredible, and the distance here is very, very short. So if the mass 2 represents the mass of this core collapsing, and this is the distance, there's an incredible amount of gravity here. We talked about the amount of gravity on a white dwarf being incredible. If you were on a neutron star, the gravity would even be more incredible, and gravity is just how much it's the force. It's kind of like your weight. Your weight is how much gravity is pulling you down. This thing, you'd be flattened instantly. But we're keeping Joe okay for a while. The gravity's okay. He could never stand on this thing. It'd be too much gravity. He'd be flattened. But we're going to keep him okay as you're orbiting around here. And you know what we're going to do is we're going to give Joe a little cell phone here. And we're going to give you a cell phone here. Remember, that's Joe. I can't erase this, but Joe's gone. There's your cell phone. You both have cell phones, so maybe you can talk to each other if you want. I don't know if you'd want to talk to him. Well, because the gravity is so high here, we have a term I'd like you to know. And the term is called escape velocity. Now, escape velocity, I'd like you to write this down. Escape velocity. Or, in other words, here's the symbol for it. V sub ESC is the velocity needed to leave a gravitational body. So I'm going to write again. In case you can't see what's right down here, I can't even tell what you're seeing on here. This computer's pointed away from me. The escape velocity is the velocity needed to leave a gravitational body. You know what the Earth's escape velocity is? It's about 7 miles a second. If you could throw a baseball straight up at 7 miles a second and ignore air resistance, it would leave Earth if it's just 7 miles a second. I mean, that's pretty fast, though. That's like from from Santa Rosa to Rohnert Park in 1 second. I mean, that's faster than any bullet travel. So if you can throw something straight up 7 miles a second, it would go out into space and not come back. From the moon, it's only about just over about a mile a second. The moon has a little less gravity, so you only have to throw something about a mile a second to leave the moon. So, but however, this thing right here, there's so much gravity that we're going to say this. The escape velocity, V sub ESC, for this thing is 160,000 miles per second. You do not have to write that number down. I'm making this number up anyway. But there's a point where it's going to be something like that. You know what that means? That means that not many things can escape this thing. You would have to go at least 160,000 miles a second to leave this. Now, there is one thing we know that can go 160,000 miles per second. There is something. And you know what that is? Light. Light goes 186,000 miles a second. So, hey, we gave Joe a cell phone. Guess what? If radio waves come from it, it can make it out. Look, radio waves going this way, make it out. Radio waves going this way, radio waves going this way. You can talk to Joe. Radio waves going this way, make it out. But look at this. Radio wave going that way. Uh-oh. Radio wave going this way. Look what happened to these radio waves. You know what happened? Is that from the surface's point of view, these radio waves are not going at least 160,000 miles a second because they're not going more straight away. If a radio wave is kind of going down towards the surface, it's not going to escape because remember, radio waves go the speed of light. They're a type of light. So you see what we have here? We have, what is the shape of this thing? Think three-dimensionally. It's a cone. It's called the exit cone. Exit cone. I'm not going to have you remember that. But an exit cone is a cone of EMR that can get get away from a surface of a gravitational body. Now, this is only a fraction of a second at a time. A fraction of a second later, you know what this thing has done? Remember we said gravity is collapsing this thing? Now watch. A fraction of a second later, this thing's even smaller. This core has collapsed. Do you see that thing right now look, isn't that smaller? That's a little bigger? That's a little smaller. So what has happened now? Now let's show Joe. Joe's right over here. There's Joe. There's his cell phone. You can show that. Let's show you in your rocket. And maybe you've moved a little bit in that fraction of a second. So here you are in orbit. I'll do it like this. You're in orbit. You're in a stable orbit around this thing. This thing, a lot of gravity here, but you're going pretty fast. You're staying in orbit around here. Let's show you. Let's show your cell phone right there. That's you. There's Joe. Now remember, gravity's collapsing this thing down. So gravity is compressing this. And this is all happening in fractions of a second, but we're slowing it down just so we can see what's going on. And again, we're talking about the core of a supergiant after the supernova, or maybe even just before. We think this thing could kind of happen right before a supernova. It may help cause a supernova. Now, what has happened is that, do you see what's happened to Joe and the surface of this thing? Because what has happened is this. This thing has collapsed. And now, isn't Joe a little closer to the center here than before? Look, because this thing's collapsing down, the surface is closer to the center. It's like taking a ball and compressing it down. Because of that, this distance has gotten smaller. And if the distance, look at gravity again, the way gravity works. The way gravity works, if this gets smaller here, the distance, if it's on the denominators, this gets smaller. Doesn't this get bigger? If this number gets smaller, that gets bigger. The force of gravity goes up. And if the force of gravity goes up, the escape velocity will go up. You'll have to go faster to leave. So now we're going to say the escape velocity equals 180,000 miles per second. You don't have to know that number. Again, I'm just making this up, but there is a point where it gets to be this. It only lasts for a fraction of a second, but there's a point where it gets to be like this. Well, at this point, isn't there still something that goes faster than that? Yeah, light. So let's see, radio waves. Radio waves are a type of light. Watch this. Radio waves going straight away, make it out. Radio waves going this way, make it out. Radio waves going this way, make it out. But watch this radio wave. Oh man, look at that. Look at what's going on here. If radio waves are not within this cone right here, they're not getting out. You see the exit cone? Look at the exit cone here. Remember that? Look at the exit cone there. What can you say has happened to it? Hasn't it gotten smaller? Because the escape velocity has gone up. Now, would you be able to talk to Joe from this position? Would you be able to get a radio wave from Joe? No, you wouldn't be able to talk to Joe. That's not a problem, though. You probably didn't even want to. But you see, no light, no EMR from this part of the surface here can get to you. Maybe EMR from here at this point could, but not where Joe is. Well, now, an instant later, let's see what has happened. An instant later, hasn't this thing collapsed even more? And now, what has happened is this. Do you see how that is now smaller than that? Look at that. You can even see, I don't know. Look, you can see it inside there. I mean, that's just to show you it's smaller, just in case there's an argument here. It's smaller. There's Joe. There's a cell phone. Gravity's still collapsing this thing. There's gravity collapsing this thing. Remember, gravity's there's nothing going to stop gravity. Gravity's going to collapse it down to pretty much no size. We're just kind of slowing this thing down. Well, we got to show you. Let's show you in your ship. There's your spaceship. This is you. This is you. Not this are you. Here you are. There you are. All right. So there you are. And you're in orbit around this thing. And now, let's see what's going on here. It has collapsed to a point now where it's even smaller, right? Do you see this distance right over here? right there. Do you see this distance? Do you see how this keeps getting smaller? Which means that gravity keeps going up. And at this point, the gravity is so strong that the escape velocity from this, to leave it, you'd have to go c. Well, what is c? C is the speed of light. There's the symbol for the speed of light, c. It's 186,000 miles per second. So at this instant, the escape velocity equals the speed of light. Now, there is one thing that gets away at this point. There is only one thing that gets away, and that is light. But only light from Joe's cell phone that's going straight away. What about light going this way? Nope. What about light going this way? Nope. Do you see what's happened to the exit cone? It's not a cone anymore. It's like an exit, what would you call that? An exit line. You don't even call it an exit line. You see, there's no more exit cone. At this instant, light only that's going perpendicular away from the surface, 90 degrees from the surface, straight up, is the only thing that can get away. So unless you were right there, you couldn't get a signal from Joe. Well, now, when the escape velocity equals the speed of light, there's a special name for this. See this radius right over here? That radius that we're talking about, that distance from the surface to the center, we call that this. All right, I'm just going to write it out. Okay. When the escape velocity equals c, the speed of light, the object, which is a core, right? This core, we're talking about a core of a dead star, has reached, I know this is kind of small writing, so if you can't see this very well, write this down. When the escape velocity equals c, the speed of light, the object, or is the core we're talking about here, this thing, has reached its two terms. Two terms we're going to talk about. One, make it big here. It's called its gravitational radius. Or in other words, r sub g. Gravitational radius. So they say the radius right now is r sub g, gravitational radius, when the escape velocity from the surface equals the speed of light. Number two, something you don't have to write down, but the person who figured this out was named Karl Schwarzschild. You may have heard of him, a physicist. So this is called the gravitational radius, but it's also called the Schwarzschild radius. But just know it as the gravitational radius. I'm going to put a star there. Gravitational radius, when the escape velocity equals the speed of light. And at this instant, only light can leave the surface. Now this is only for a fraction of a second too, because guess what's going to happen an instant later? Yeah, it's going to collapse inside of its gravitational radius. It's going to get smaller than that radius. So let's look at it then. Now there's a problem right now we're going to come to. Here's the problem. Now let me show you this. I'm going to try to show. You remember that? The gravitational radius, that radius right there? What I'm going to do is I'm going to kind of show it right here. Oh, this pen is terrible. No, I'm okay. I have one right here. Thank you. And I'll just use, this one right here. So right here. So there it is. So do you see that line, this line here? The gravitational radius. I just shown it right there. Now, which means this. I'll show you the size of this thing. This is kind of terrible here. This kind of dotted thing right here should be kind of like a circle. That was the size of it when the escape velocity equals the speed of light. But you know what the thing has done now? It has now collapsed inside of its gravitational radius. It's smaller than the size of it when the escape velocity equals the speed of light. Which means this. This is weird. Now here's Joe. There's a cell phone. I could show Joe and a cell phone there. Now, because it is now smaller than the gravitational radius. Even though the gravitational radius now doesn't even represent the radius of it, this thing is actually smaller because gravity's collapsing this down to pretty much the point right here. Do you know what the escape velocity from this would be right now, from this core that's collapsed down inside of the size when the escape velocity equals the speed of light? The surface is not there anymore. The surface is here, which means the escape velocity is greater than c. Now, that's a greater symbol. I'm just going to write it for you. The escape velocity is greater than the speed of light. if the escape velocity is greater than the speed of light for this thing right now, for that core that's collapsed down, and it still keeps collapsing. You know what that means about light? That means that light that's going 186,000 miles a second and has to go faster than that to leave a cell phone, like radio waves from the cell phone, guess what? Get pulled back. Not just radio waves, every type of light. So you know how this is going to look then? How is it going to look? Black. This whole thing would be a black sphere like this. I mean, I'm not going to show it as dark as it would be, but it would be a black sphere. When the escape velocity from, and I can kind of show that there, when the escape velocity is greater than the speed of light, nothing leaves from it. And guess what it's called now? It is now called a black hole. A black hole is, I'll tell you what it is. It's a region. It's like it's not even an object anymore. It's just that this whole region is called the black hole. It's a region where the escape velocity is greater than c. Or in other words, it is an object which has collapsed inside its own gravitational radius. Because how isn't this object now smaller than the gravitational radius? So you see this? That's what a black hole is. It is a region. It's not necessarily an object. We're going to talk about what that object is. There's still a core there that's collapsing down to pretty much nothing. But the black hole is the region where the escape velocity is greater than the speed of light, and there can be no light coming from that region. Now, there's something else here that I would like you to know. There is the edge of the black hole. The edge, and think of three-dimensionally. I'm showing you kind of like a circle here with dark circle. Really, it's going to be a sphere, a black sphere. And it's going to have an edge. The edge of the black hole, the theoretical surface of the black hole is called they named a movie after it. A movie from 20 years ago or more. I don't know, I didn't see it. Supernatural movie. Can't handle those movies. Supernatural, I don't deal well with those. Some of you have seen this movie. Some of you know the name. The theoretical edge or surface of the black hole is called the event horizon. Good to know, event horizon. The theoretical edge or surface of the black hole. I'll say it again. I'm not going to write it here. It's a mess anyway. The event horizon is the theoretical edge or surface of the black hole. It's not a physical thing. It's a boundary. At the event horizon, there's not something you can touch there. It's a place where just right at the event horizon, the escape velocity equals the speed of light. And it's like, that's right at it's at the gravitational radius from the very center here. So the event horizon is the boundary between where the escape velocity is greater than the speed of light inside the black hole and where the escape velocity is less than the speed of light, which is outside the black hole. Right at the event horizon, the escape velocity is the exact speed of light. Right at the boundary of the black hole. And if you're inside of it, if you're within the event horizon, you will not know about any events there. It's the horizon of events. So it's called the event horizon. And if you're within the event horizon, you're within the black hole. And this object, this collapsing core is eventually going to collapse to a point called a singularity, a point of infinite density, possibly. Depends on if the black hole is rotating or not. So this core is going to keep collapsing and collapsing and collapsing, and it may even disappear from our universe in a different dimension. It's going to be somewhere, but it may not be part of our universe. We're going to talk about relativity starting like next class, and you think this is weird? Wait till we talk about relativity. So now and I'm going to talk more about these terms too next time with a PowerPoint. We're going to do a PowerPoint next time, which is always a little easier. Now remember, Joe's gone here, and so but there is someone more important than Joe, which is everyone. But remember if we go back to this, there's something I didn't put in this picture here. The most important person in this picture was who? Well, Joe's here. Remember you? Don't forget about you. You're important. I'm going to show you. Well, there's your ship. Remember your ship that was in orbit around this collapsing core? Now, it's become a black hole now. Now, I've got to show you. Remember, here you are with your cell phone. You can't talk to Joe anymore. That's okay, though. Now, when this thing becomes a black hole, what happens to you? I know a lot of people say, it becomes a black hole, you get sucked in. Well, let's think about this. Remember the force of gravity? It is determined on mass 1 times mass 2 over distance squared. Sorry about the mess there. Now, Joe got pulled in. Joe was on a surface that kept getting closer, but let's think about you. Did your mass change? Let's say mass 1 is mass u. Don't you have the same mass, same material? Your rocket's the same material. There's nothing changed here as far as material. So look at this. So for you, mass 1, that's you, same. What about mass 2? The mass of this collapsing core, the black hole. Remember we said at the beginning it was 10 solar masses? Did that change? No. It just collapsed down. It's like taking cotton candy and compressing it. Are you going to get more cotton candy if you compress cotton candy? No. Are you going to get less? No. You're just going to have it smaller. So really the density's gotten higher, but the mass is still the same. So guess what? Mass 2, the mass of black hole, same. Now look at this. What about the distance from the center of you to the center of this collapsing core? Look at this. See this distance there? Look at that. I don't know. What does that look like? I'm going to say here it's like 5 inches or so. Well, let's look at it here. Let's look at a past picture. Well, look at this. About 5 inches. Look at this. 5 inches. Huh. Look at this. This is the very beginning. Do you see what's happened for this distance between you and the very center? Even though this thing has collapsed down, hasn't the distance from you to the center stayed the same? In every one of these pictures, to the center, it's for you to stay the same. Now, you to the surface is changing because the surface is getting close to the center. But from the distance from you to the center, it's the same. So you know what? Look at this. Same. If distance squared, it doesn't matter. If that distance is the same, distance squared is going to be the same. Same, same, same. Which means this for you, same. Which means what happens to you? Nothing. You're fine. Joe's not, but you're fine. Do you see black holes don't suck everything in? I mean, if we're far enough away from a black hole or in orbit around a black hole, you're fine. Only if you get really close, or like if you're very close to the surface or on the surface, you're in big trouble because you keep getting very, very close. Eventually you're going to be in the black hole. But if you stay at a distance away, I mean, there are a lot of black holes out there. Are they sucking us in? No. Earth's fine. Sun's fine. So do you see when holes don't suck? Unless you're really close to them. Really, only if you're very close to them is it a problem. And isn't that what you maybe thought when you sent Joe in? I know, even though I couldn't hear you sending Joe in, I know you did it. Everybody does it. Joe always gets sent in. And isn't that what you were counting on when Joe got sent in? That Joe probably won't make it, and you might? Well, guess what? You were right. You did a good job. Sent Joe in. You stayed out. You're safe. That's it for today. We'll talk to you next time.
Goodbye.
Okay.
Did it work?
I don't know. Gotta find out.
Well, how long was it?
I don't know. I was working.
I don't